Hello everyone, welcome to MK Academic Solutions. So in this video I am going to explain you about the equilibrium. So this is the topic from the chemical equilibrium chapter. This is the second lecture on the chemical equilibrium. In the first lecture I have explained you already what is the type of reaction and reversible reactions and irreversible reactions. Okay, this lecture is a continuation for that one. So now in this I am going to explain you about the equilibrium. Okay, so first of all, equilibrium. Before we are discussing about the equilibrium, so let us recap what is a reversible reaction. What is a reversible reaction? So reversible reaction. Reversible reaction means the reaction which occur in both forward and backward direction, that is called what? Reversible reactions. Okay. So the reactions which occur in both forward and backward directions are called reversible reactions. So here generally if reactant R is converted into product, conventionally it is called forward reaction, and whereas if product again convert into reactant, that is called backward reaction. Backward reaction. Okay. So here what is a forward reaction means reactant is converted into product, that is forward reaction, and product is converted into reactant is called backward reaction. Okay. So here generally in a reversible reaction the reactant can be converted into product and again product can be converted into reactant. Now let us consider, we are going to start with the reactant. We are taking only the reactant R. So at initial time only reactant is converted into product. Why? Because there is no product at initial time. Okay. As time proceeds, what will happen? Some amount of product also is going to be formed. That product slowly starts to convert into reactant. Means here initially the reactant is only reactant is present. The reactant is converted into product, that is called forward reaction. At initial condition, which reaction we are having? Only forward reaction. If you start with only reactant. Okay. So as time proceeds, what will happen here? Some amount of product is also going to be formed. That product slowly converted into, again it starts convert into reactant. Okay. So at initial time the rate of forward reaction, at initial time the rate of forward reaction is very high. This is the rate of reaction at initial time. As time proceeds, the rate of forward reaction is going to decrease. Gradually it decreases. So this is what? Forward reaction. Forward reaction. Okay. So forward reaction, as time proceeds, what will happen? At initial time the rate of forward reaction is very high. Why? Because at initial time we are going to start with only reactant. Okay. So at initial time rate of forward reaction is very high. As time proceeds, rate of forward reaction slowly decreases. Why? Because the concentration of reactant is going to be decreased. At initial time the rate of backward reaction is 0. Why? Because at initial time there is no product. We don't have any product at initial time. So but as time proceeds, some amount of product is going to be formed, that again converted into reactant. Okay. So means as time proceeds, the slowly the forward reaction decreases, but the slowly backward reaction is going to increase. At a particular time interval, or after reaching at a particular time interval, the rate of forward reaction will become equal to rate of backward reaction. So it is what? Backward. Okay. It is the backward reaction. Backward reaction. And it is the forward reaction. So after reaching a particular time interval, what will happen children here? Rate of forward reaction will become equal to rate of backward reaction. So here rate of forward reaction is equal to rate of backward reaction. Such condition is called equilibrium. This condition is called what? Is called equilibrium. Okay, equilibrium. So now how we can define the equilibrium? How we can define the equilibrium? So in a reversible reaction, if rate of forward reaction is equal to rate of backward reaction, that is called what? Equilibrium. Okay, so simply what is the definition of equilibrium? If rate of forward reaction, if rate of forward reaction is equal to rate of backward reaction, rate of backward reaction, that is called what? Equilibrium. Is called equilibrium. Okay, so now we understood what is the equilibrium and where equilibrium is going to be exist. Okay, now let us see the characteristics of equilibrium. Okay, what are the characteristics of equilibrium? See here, equilibrium can exist in where? Only in reversible reaction. Only in reversible reaction. Why? Because in reversible reactions only we are having both forward and backward reaction, whereas in irreversible reaction only we observe forward reaction. And at equilibrium the concentration of reactants and products will become constant. Okay, so at equilibrium the concentration of reactant and product will become constant. Let us assume, so one hypothetical example here, reactant is converting into product. Okay, so here we are going to take the concentration versus time graph, concentration versus time, concentration versus time. So we know in any chemical reaction, as reaction proceeds, means as time proceeds, the amount of reactant is going to be decrease and the amount of product is going to be increase. Okay, so here concentration, this is the concentration of reactant at initial time and this is the concentration of product at initial time. Okay, so now let us assume this is the concentration of reactant R, it is going to be decreased gradually, and the concentration of product, okay, the concentration of product increases gradually, and after particular time interval what will happen? There is no change in the concentration of reactant as well as the concentration of product. Okay, there is no change in the concentration of reactant as well as product. Okay, so now in this particular condition the concentration of reactant, this one at equilibrium, and the concentration of product is, this is at equilibrium. So here what happened? The concentration of reactant and products are constant, but what about the relative concentration of reactant and product? So here when you see the relative concentration of reactant and product, product is having more concentration than the reactant. However, after reaching equilibrium there is no change in concentration of reactant and product, that is the meaning of constant. Or else sometime the equilibrium may also exist likewise. Okay, so initially the concentration, this is the concentration of reactant. So here reactant concentration slowly it decreases and it become constant at a particular time, and the concentration of product initially it is 0, the concentration of product initially it is 0, as time proceeds slowly it increases, after reaching equilibrium the concentration of product is also constant. Okay. So here also the concentration of product is constant. Okay. As time so here when you compare the relative concentration of reactant and product, so in this particular equilibrium reactant is have more concentration than the product. Okay. However, they are constant after reaching the equilibrium. And next, when you see the one more probability here, that is, so this is the concentration of reactant. So as time proceeds the concentration of reactant is going to be decrease, and at a particular time it will become constant, means there is no change in the concentration of reactant. And product, this is the concentration of product. As time proceeds the concentration of product is going to be increase. So after reaching that particular time interval there is no change in the concentration of reactant. Okay. There is no change in the concentration of reactant and there is no change in the concentration of product. So in this particular situation what we can understand, what is the relative concentration of reactants and products at equilibrium. Reactant concentration of reactant is equal to concentration of product at this particular time, at this particular graph. Means in equilibrium, what we can understand in equilibrium, the concentration of reactant and product are constant. Means at equilibrium the concentration of reactant equal to concentration of product also possible, the concentration of reactant is greater than concentration of product also possible, or the concentration of product is greater than concentration of reactant is also possible. Means these type of conditions are possible, but however when you see in all these graphs the concentration of reactant and products are what? Constant. Okay. And what about the rate of forward reaction and rate of backward reaction? So rate of forward reaction is always equal to rate of backward reaction, but what about the concentrations? Means they are constants. Okay. Right. Next, the temperature, pressure, color, all these extensive properties will become constants, and free energies also, all these properties will become constant, means they are not at all going to change at equilibrium. If you change the temperature, pressure, the equilibrium going to be disturbed. Okay. Next, catalyst cannot alter the state of equilibrium. So here what is the catalyst? Catalyst we know already, it increases the rate of reaction. Means catalyst can increases the rate of forward reaction as well as rate of backward reaction with equal. Means catalyst can equally increases the rate of forward reaction and rate of backward reaction. That's why catalyst cannot alter the state of equilibrium. See, in absence of catalyst, equilibrium is going to be attained within 10 minutes. Like that you consider, when you add a positive catalyst, the equilibrium may exist within 5 minutes. Means what catalyst can do, catalyst can decreases the time or speed ups the equilibrium. Within the short time only the equilibrium is going to exist in presence of positive catalyst. Okay. So it speed ups the attainment of equilibrium. Catalyst speed ups the attainment of equilibrium. Equilibrium by increasing the rate of forward reaction and rate of backward reaction with equal rate. Next, if any gases are involved in the equilibrium exists only if any gases are involved, equilibrium exists only in closed container, not in the open container. Why children? Why it is? Why? Because if you use open container, what will happen? The gases are going to be expelled continuously. So only the one direction reaction only will occur. Okay, means there will be no possibility of exist of equilibrium. For example, you take CaCO3. Upon heating, it will give us calcium oxide plus CO2 gas. If you do in the open container, what will happen? The CO2 gas continuously it is going to be expelled. Means here we are the product is going to be removed. So when you remove the product, again the calcium carbonate is converted into again calcium oxide and carbon dioxide. Here for the reversible reaction, carbon dioxide is not available. That's why the reverse reaction will not take place, only forward reaction take place. That's why we should use only closed container but not the open containers. Okay. Next, so this is about the some characteristics of equilibrium, and also one more thing here, the concentration of reactant and product present at the state of equilibrium, that is called equilibrium mixture. Okay, what is the equilibrium mixture? Okay, so equilibrium mixture, what is equilibrium mixture? Okay, what is the equilibrium mixture? Means the amount of reactant and product present at the state of equilibrium, the amount of or the concentration of reactant, the concentration of reactant and product present at the equilibrium is called equilibrium mixture. Equilibrium is called equilibrium mixture. Next, one more important point, equilibrium mixture. Next, equilibrium is dynamic in state. Equilibrium is in a dynamic state. Equilibrium is dynamic in nature. Means what is the meaning of dynamic? Dynamic means, children, here always forward and backward reaction is going to be take place continuously after reaching equilibrium also. That is known as what? Dynamic equilibrium. So here reactant is always converted into product is always converted into reactant. Means here both forward and backward reactions are not at all going to stop after reaching equilibrium, but they are taking place continuously after reaching of equilibrium also. Such type of equilibrium is called what? Dynamic equilibrium. So here both forward and backward, both forward and backward reactions takes place continuously. Takes place continuously without stopping. So that's why it is known as what? Dynamic equilibrium. See here how we can prove this chemical equilibrium is a dynamic process. Okay, see, for example, we are going to take the two equilibrium mixtures. 2NH3 is gives rise to N2 plus 3H2. Let us consider it is the first equilibrium mixture 1. It is the equilibrium mixture 1. Equilibrium mixture 1, and second one 2ND3 means here hydrogen is replaced with the deuterium. Hydrogen is replaced with what? Deuterium. And here what are the products? Here you will get N2 plus 3D2. It is the equilibrium mixture 2. Okay, it is equilibrium mixture 2. Okay, so now what I am going to do now, I am going to mix the both equilibrium mixtures. When I mix the both equilibrium mixtures, when both are mixed, we get NHD2 also will get, and NH2D and HD. These are the substances we are going to get. Means here in this equilibrium mixture what we are having? Only NH3 and N2 and 3H2. In this what we are having? ND3, N2 and D2. But after mixing the equilibrium mixtures, what are the substances again we are going to see? NHD2, NH2D and HD. These are the substances we are going to see. How these substances are going to be formed? So here already I told you they are what? Dynamic, means the both forward and backward reaction is going to be take place. So whenever you mix this both equilibrium mixtures, how a backward reaction may take place also? Here 2H2 plus D2 and plus N2, they may combine, they produce what? 2NH2D. So like that reaction is possible, means they are going to be combined like this, or else hydrogen plus deuterium they combine, they will give us HD. And also 2D2 plus H2 is gives rise plus N2. Plus N2 gives rise to 2NHD2. So these are the substances we are getting because of what? Continuously reactions are going to be take place here. Continuously both forward and backward reactions are going to be take place. Okay. So here one more important thing, that is equilibrium can also exist in the physical process also. Equilibrium can exist in where? Physical process also. See for example here solid to liquid, solid to liquid, okay, and liquid to solid in a closed container, or you can take liquid to gas, or sometime you can take the sublimation also, solid to gas or gas to solid, sublimation, and liquid to gas evaporation, solid to liquid melting, liquid to solid it is freezing or freezing, gas to liquid it is condensation. In these all process also we observe a existing of equilibrium. These are all what? Physical equilibrium. These are all what? Physical equilibrium, physical equilibrium. And if equilibrium exists in chemical reactions, that is called what? Chemical equilibrium. If equilibrium exist in chemical reactions, that is called chemical equilibrium. Okay, right? See, for example, H2 plus I2 is gives rise to 2HI. This is the chemical equilibrium. SO2 plus O2, 2SO2 plus O2 is gives rise to 2SO3, chemical equilibrium. PCl5 is gives rise to PCl3 plus Cl2, etc. All these are examples of what? Chemical equilibrium. Okay, so now we have understood what is the equilibrium, what are the characteristics of equilibrium. Okay, now let us see. So these are all the characteristics of equilibrium. Now let us see the some more important topics, that is active mass. So from here onwards the topic is very important. So listen carefully. Okay, so the concentration of reactants and products. So what is the active mass? First of all, what is the active mass? Is nothing but concentration. What is active mass? Active mass is nothing but what? Concentration of reactants and products in the chemical reactions are called what? Active mass. So here active mass, this is active mass. Active mass represented with molarity, normality, mole fraction, formality, mass percentage, volume percentage, etc. what we have learned in the solutions chapter. All these are the methods we use to express the active mass. But generally the active mass is represented with what? Partial molarity, like this square bracket. This is square bracket represent what? Active mass. After the square bracket, if you are going to keep EQ, that will become active mass of the substance at equilibrium. So this is what? Active mass at equilibrium. Okay, and sometimes this active mass also represented with what? Partial pressure. So partial pressure is important when gases are involved. So when the partial pressure is important is when gases are involved, the partial pressure is important. Okay, right? Next, the active mass of pure solid, the active mass of pure solid, active mass of solid and pure liquid is unity. Active mass of pure solid and pure liquid is unity. Why? Because see, this mass of pure solid is an intensive property. How much volume of the container you are going to change, also the volume of the solid is not at all going to be changed. How much volume of this container you increase? For example, here I took the 50 grams in 100 ml flask, and here I am going to take the 1000 ml, and the same substance I am going to keep here. So it will be what? Again 50 grams only. Means here the volume of solid is not at all going to be changed according to the volume of container, means the volume of the solids is fixed. Volume of solids is what? Fixed. Means let us consider, okay, not like in grams, let us consider it occupied how much volume. Let us consider 10 ml volume it is occupied. It is also occupied how much? 10 ml volume. Means even though you change the container, what will happen here? The volume of solid and even volume of liquid also is not at all going to be changed. That's why the active mass of solid and pure liquid is what? Unity 1. 1 we will take, but not for gases, but not for gases. Why but not for gases here? Why? Because if you change the volume of container, volume of gas is also going to be changed. So here we know already volume of gas is equal to what? Volume of container. Why? Because gas molecules move very freely and they are not at all having any fixed volume. That's why if the volume changes, the volume of gas also changes. That's why here the active mass of pure gas also we are not at all going to take a unity. Why? Because it changes along with the volume of container. Okay. So these are the some important points about the active mass. Okay. And the next term, that is law of mass action. See here, what is the law of mass action? Active mass, not this is law of mass action. Law of mass action. Okay. Law of mass action. Law of mass action. Law of mass action. Law of mass action. Okay. So law of mass action. So what is the law of mass action? Okay. So what is the law of mass action? First of all, it was proposed by it. So it was proposed by the Guldberg and Peeves. According to this law of mass action, the rate of chemical reaction is directly proportional to the product of concentration of reactants raised to their power stoichiometric coefficients. Okay. See, for example, here I am going to take a hypothetical reaction. A hypothetical reaction. Okay, right. Let's change the color. Okay. Here I am going to take a hypothetical reaction. A moles of A plus B moles of B gives rise to C moles of C plus D moles of D. This is an hypothetical reaction. Okay. So let us consider it is the forward reaction. What it is? Forward reaction, and this one is the backward reaction. So for forward reaction, what is the rate of reaction according to law of mass action? So rate rate forward is directly proportional to concentration of A power A, concentration of B power B. Okay. So this is known as what? Law of mass action. So law of mass action, what it is telling children, rate of a reaction is directly proportional to concentration of reactants. Product of concentration of product means multiplication here, product of concentration of reactants raised to their power stoichiometric coefficients, or the same manner rate of backward reaction is proportional to. So now these are converting into reactants, that's why concentration of C power C into concentration of D power D. So this is known as what? Law of mass action. Okay, right? So now here to remove this proportionality we are going to keep constants, that is rate forward is equal to rate constant for the forward reaction into A power A, rate constant B into B power B. Rate constant of rate of backward reaction is equal to rate constant of backward reaction into concentration of C, concentration of C power C, concentration of D power D. Okay. So now at equilibrium, okay, we know, so this is what? Law of mass action. What is the law of mass action? So rate of, according to law of mass action, the rate of a chemical reaction is directly proportional to the product of concentration of reactants raised to their power stoichiometric coefficient. This is for forward reaction, and for backward reaction is what? Rate of backward reaction is proportional to product of concentration of products raised to their power stoichiometric coefficients. This is known as what? Law of mass action. Okay. So now let us write the law of mass action for some examples. Let us take H2 plus I2 gives rise to 2HI gas. So for this, how we write the law of mass action for forward reaction? Law of mass action for forward, and this is the backward. For forward reaction, rate of forward reaction is equal to K into H2 gas power 1, I2 gas power 1. For backward reaction, rate of backward reaction is equal to Kb into Hi gas power 2. Okay. So this is what? Law of mass action. And let us take one more example also. Calcium carbonate CaCO3 in the solid state. CaCO3 in the solid state gives rise to CaO in the solid state plus CO2 in the gaseous state. Okay. So for this rate of forward reaction is equal to K into CaCO3 power 1, and backward reaction CaO and CO2 power 1. But here what is CaCO3 is solid. If any solid and pure liquid are involved, what we will do children? We will take their molar concentrations, or their concentrations will take as the unity. Okay, we will take as what? Unity. That's why therefore rate of forward reaction is equal to K into 1. Here also rate of backward reaction is equal to K into only CO2 power 1. Likewise, we are going to write the law of mass action. Okay, this is about what? Law of mass action. And come to the last topic of this lecture, that is equilibrium constant. Okay, so what is equilibrium constant? Equilibrium constant is what? It is the ratio of the rate constant of forward reaction to rate constant of backward reaction, or else the ratio of product of concentration of products raised to their power stoichiometric coefficients to product of concentration of reactants raised to their power stoichiometric coefficients at equilibrium. This point is very, very important, should be noted. Okay, this also at equilibrium point is very important. Okay, so now, so just take that hypothetical equation, A moles of A plus B moles of B gives rise to C moles of C plus D moles of D. Okay, now let us apply the law of mass action for forward reaction and also for backward reaction. This is the forward and this is the backward reaction. Let us apply the law of mass action. Okay, so rate of forward reaction is equal to Kf into concentration of A power A, concentration of B power B. Rate of backward reaction is equal to Kb Kb into C power C and D power D, right? Okay, so now at equilibrium, we know already rate of forward reaction is equal to rate of backward reaction. Rate of forward reaction is equal to rate of backward reaction. Therefore, if rate of forward reaction is equal to rate of backward reactions, these two terms will become equal. Okay, so therefore, what I can write, children, here, Kf A power A B power B equal to Kb C power C D power D. Okay, now let us bring the same terms at same side. Therefore, Kf by Kb is equal to concentration of C power C, concentration of D power D by concentration of A power A, concentration of B power B. So here Kf by Kb is called equilibrium constant Kc. Okay, we already know. So the rate constant of forward reaction to backward reaction, the ratio of rate constant of forward reaction to backward reaction is called equilibrium constant Kc. So that equal to, okay, that equal to concentration of C power C by concentration of D power D by concentration of A power A, concentration of B power B. This is the Kc. Okay, equilibrium constant. When you write the Kc means when you take the molar concentrations. When you take the molar concentrations, we will write the Kc. So when you write the Kp means instead of molar concentrations, we will take the partial pressure. So partial pressure of C power C into partial pressure of D power D by partial pressure of, okay, so let, or else we will write this set. Okay, Kp, when we write the Kp, we will take the partial pressures. Partial pressure of C power C into partial pressure of D power D by partial pressure of A power A into partial pressure of B power B. So if you take the partial pressure, we write the Kp. If you take the molar concentrations, we write the Kc. Okay, so this is about the lecture number 2. Okay, so once again if you revise this concept and go through the textbooks and write the neat notes so that you can get the clarity over this concept. Okay, thank you for watching.